Okay, so that's uniaxial stress and uniaxial strain and shear stress and shear strain. There's another elastic constant called Poisson's ratio as well. And let me see if I brought my little thing here. Hang on. I forgot to get my little demo out. Oop. Where did it go? Not that, not that. Here we go, here we go. Okay. Okay, so I brought a little rubber band with me here. And maybe if I stand in front of here, you can see. So the band is a certain width, right? And I'm sure you've all done this yourselves. If you pull on it like that, it gets skinnier, right? So you pull on it, and the width of it changes. Poisson's ratio relates how much strain there is in this direction and how much strain there is that way on, okay? So it's actually the ratio of the strain this way to the strain that way, okay? So we also want to define Poisson's ratio. And it's given the symbol nu, the Greek letter nu. And it's a negative ratio of the strain. And the reason it's a negative is because when I'm pulling on the thing, it contracts this way. So if I make it a negative ratio, I end up with a positive value for that. So I'm going to say it's the negative, and I'm going to call it the lateral strain. So the strain in a direction orthogonal to where I'm applying the load. So the lateral strain divided by the strain in the direction of the applied uniaxial stress. Okay. So say I defined some x and y axes like this, and I'm going to draw a bar, and we'll look at that transverse or lateral strain and define the Poisson's ratio a little bit more exactly. So say I have my bar, not quite there, I need a little bit more room. Okay, so that's my bar initially, and this length of the bar is Lx naught. And this height of the bar here, I'm going to call Ly naught. Okay. And now when I pull on my bar, it's going to get a little longer and a little narrower. So it's going to get, oops, something like that. Say I pull on it with some load P, like that. And now the new length is going to be Lx, and this new width here is going to be Ly. Okay? So the idea is as I pull the bar, it's going to contract sideways, and that the strain in the y direction is going to have the opposite sign of the strain in the x direction. So here, my Poisson's ratio is then going to be the ratio of the strain in the y direction relative to the x direction. So that's Ly minus Ly naught over Ly naught divided by Lx minus Lx naught over Lx naught. Or I could say that's equivalent to minus delta y over Ly naught divided by delta x over Lx naught. Okay? So as I pull on my bar in the x direction, it's getting narrower in the y direction, and I haven't drawn it because I can't draw into the bar, but it's into the board, but it's also getting narrower in the z direction. Okay, so if it's isotropic, it's getting narrower by the same strain in the z direction as it is in the y direction. Okay, and then I should also say that the Poisson's ratio, nu, is dimensionless. Okay, so strain has no dimensions. It's the ratio of one strain over another, so that's not going to have any dimensions either. So the Poisson's ratio is dimensionless. So I wanted to, oh, yeah?
If the material is isotropic, is there a set relationship between like the strain x and the strain y, or would they be different?
Well, that is the Poisson's ratio. That is, you know, if you're pulling in one direction, how much contraction you get the other way, that is the Poisson's ratio. But if the material is isotropic, it turns out there are relationships between the Young's modulus, the Poisson's ratio, and the shear modulus, and we're gonna get to that. Okay. Okay, so some typical values of nu. So for steel, nu is 0.28. For aluminum, 0.33. For glass, it's 0.25. For rubbers, the value's close to a half, but a little less than a half. So 0.45 to 0.49 would be typical. And for isotropic materials, apart from rubbers, the Poisson's ratio is very often near to 0.3 or 0.33, something like that. So if you didn't know what the Poisson's ratio was for an isotropic material and you knew it wasn't a rubber and you had to guess, 0.3 would be a pretty good number to guess. Okay. So I have a little demo-y thing I wanted to show you. I brought some of my honeycombs with me because honeycombs have some unusual values of the Poisson's ratio. So these are not isotropic, so these are not going to be in that neighborhood of those values there. But if I have my little regular hexagonal honeycomb and I load that, so say I load it this way on, it has a Poisson's ratio of 1. Okay, so if I have a certain strain this way, it has the same strain out that way. And this guy here, let me see if I can get the overhead set up so you can see it a little bit better. You can actually make honeycombs that have negative values of the Poisson's ratio. And that one there has a negative value. So let me see if I can make this work. That's in. There's the little doodah. There we go. Okay. Oh, okay. There we go. Is that? Yeah, that's good enough. Okay, so if I take this and I squeeze it like this, can you see how I'm pushing this way, but it's also contracting that way? So the fact that this strain, let's say that's the x direction, and that strain in, say, the y direction, they're of the same sign because I've got the negative in the Poisson's ratio, it's going to have a negative value. So that's something that's very unusual, and it's the particular arrangement of the cells in this honeycomb that gives you that. So that's kind of an interesting little thing.